Okay, so what I'd like to talk about this time is your dissolved oxygen lab. So in the paperwork for the dissolved oxygen lab, you have this table with this graphic at the bottom. So go ahead and print out this table with the graphic. And what you also probably would like to do is go ahead and cut and paste that graphic to a separate piece of paper and blow it up just a little bit. I just clicked on it and right click on it and copy the image and then copy it to a Word document and just blow it up a little bit. It makes it a little bit easier to draw on if you can. So go ahead and print those out. And what we're talking about here is we're going to talk about dissolved oxygen and why dissolved oxygen is important and how various types of water as well as different temperatures can affect the dissolved oxygen. Now, dissolved oxygen is very important to aquatic organisms because it keeps them alive. They breathe the oxygen out of the water, just like we breathe the oxygen out of the air. They have to process that oxygen either through their skin or through their gills or some other formation that they have if they're some other type of aquatic organism. So pollution can affect the dissolved oxygen in the water in a number of different ways. So we can either reduce the dissolved oxygen in the water via biological oxygen demand. We talked about that in the pollution. The other way that it can be reduced is by temperature. So one of the things we're going to look at on here is how does temperature affect dissolved oxygen? Most people think, oh, dissolved oxygen is just there all the time. But there is a property of gases that allows them to saturate a solution more easily if the solution is colder, and to diffuse or leave the solution if the solution is warm. Okay, so and it also is also affected by pressure, but we're not going to deal with pressure in this particular one because at the Earth's surface, the pressure of the water at the surface is pretty much the same as the pressure we feel at sea level. Now, if we're talking about deep ocean, the deep ocean is going to have both the temperature and the pressure to deal with. Okay, so here's the properties we're talking about. Temperature is inversely related to saturation of the solution. The colder the water is, temperature's going down, the greater the saturation or the greater the amount of dissolved oxygen that will be able to stay in the water. Okay, that's the same for any gas. Gases at lower temperatures are going to be able to be dissolved in the solution at a higher rate. And the opposite is true. If the temperature goes up, then the gas is going to go down. The amount of gas being held in the water or in the solution is going to go down. So the rule of thumb is temperature goes up, dissolved or solubility goes down. Temperature goes up, solubility goes down. Temperature goes down, solubility goes up. So the two are inversely related. Okay, so what we are going to look at is on this data sheet we have, not only do we have several different temperatures that things were done at, okay, but we also have a couple of different types of solutions. We have a saltwater solution, we have a turbid solution. Turbid, remember, means the ability to see through it, the suspended particles. So how does suspended particles affect dissolved oxygen? Okay, we have a hot water, we have a cold water, okay, we have initial algae, which basically means that the initial conditions of the solution before we expose them to light or put them in the dark. So these last three are related to each other, and we're not going to talk too much about that particular thing. What we're going to concentrate on here is the hot and cold water, the turbidity, and the salt, and see how that affects our dissolved oxygen rate. Now, at the bottom of this, you're going to see where it says the average DO, okay, and it's in bold, and I've put a square around mine right there. So you're going to use the average dissolved oxygen level, and then you see three temperatures underneath that. Okay, what I want you to do is go ahead and average those three temperatures. Now I've already done that on my sheet here. So in the first one we had 16, 18, 16. Well, if I take the average high and low from that, I get 17, right? Okay, so I'm going to take the high and low from here, 20 to 16, and so the average is 18. And I'm going to take the high and low here, 14, 15, so the average is 14.5. And then finally down here, 17, 17, and 17. All right, so make sure you take those averages before you do this thing down here, okay? All right, so once you have your averages done, what you're going to do is with your blown up particular graphic, okay, we're going to be looking at the temperature from up here. So you're going to find the temperature on this scale, and you're going to find the dissolved oxygen on this scale. All right, so I've marked the first point. The first point said 8.4 parts per million dissolved oxygen, and the temperature, the average temperature for that group was 17. So I marked a dot there at 17, and I marked a dot here at 8.4, and then I took my ruler and I connected those two. Okay, so I'm going to show you down here, point you down here a little bit. Hopefully you can see my sheet here. Okay, so I'm going to do the next one on my sheet so you can follow along. All right, so the next one says that in turbid water, the dissolved oxygen is 8.8. So here's 8, 8.5, 6, 7, 8. 8.8 is right there. And the temperature for that one is 18 degrees. So here's 15, 16, 17, 18. Okay, so now I'm going to take my ruler and I'm going to connect the 18 with the 8.8. Okay, and I'm going to draw a line. Make sure your pencil's pretty sharp because you don't want to draw too wide a line. Oop, I'm a little off there. Let me try that again. All right, and it crosses right here. Okay, so that is at 80. This point is 90. That's 95, so I'm about halfway between 90 and 95. So I'm going to say that this particular point right here is 92.5% saturation. Okay, so did that make sense how to use the nomograph? Okay, that's what this thing is called, a nomograph. All right, so I found my temperature up here. I found my dissolved oxygen number down here, and then I crossed over at this point right here. So I got 92.5. So I'm going to go ahead and put that down on my table, 92.5 for the second one. Okay, that was the turbid water. And for my first one, I got 85. So 85, and these are in percent. So just 85%, 92.5%. Okay, see what I got there? All right. All right, so we're going to continue doing that. And yes, I want you to go ahead and calculate those for the initial light and dark, but we're not really going to pay too much attention to these end ones over here. What I'm going to do is concentrate on these first four. All right, so go ahead and do those, get those numbers out, and then I want you to graph those numbers. All right, so you're going to take the temperature and the percent solution, percent saturation. Okay, so the temperature is going to be your independent variable, right? So the independent variable always goes on the x-axis, right? And the dependent variable, the one that's depending on the temperature, is going to go on the y-axis, okay? But I only want you to graph the first four, okay? I don't want you to worry about the initial light and dark. Why not? Yeah, that's right. They're all the same temperature, so it doesn't really tell us anything. We're looking at how does temperature affect dissolved oxygen. So we're not going to worry about the initial light and dark numbers on this one. So just graph the first four, right? So when you graphed those first four, you're going to look at, and it's going to be what kind of graph? Are we talking changes over time, parts of a whole, or a comparison? Comparison, right. So we're looking for a bar graph. So we're just simply going to compare the percent saturation with the temperature. Okay, and we're going to ignore for the moment the fact that it's salt water and turbid water and cold water and hot water. We're just going to look at the temperatures and the dissolved oxygen percent saturation that we got. Okay, and then once we've looked at that on the graph, we want to answer that question. What affects the dissolved oxygen? The percent of dissolved oxygen dissolved in the water. Okay, so is there more dissolved oxygen in the water when it's cold, when it's hot, when it's salty, when it's turbid? Okay, so that's the question I want you to answer, and that's how to do a nomograph. Okay, and there are a few more questions that go with it. Okay, now when you look at saturation, right? Saturation is the amount of the ability of the water to hold the dissolved oxygen. It's not the amount of dissolved oxygen that can be dissolved. It's already in there. And that means that there can be more or less dissolved oxygen that goes in there. So when we think about dissolved oxygen levels, okay, it's going to look a little different when you start thinking about the percent that's already in there, okay, versus the percent that could get in there, right? So, and notice something about this graph. It goes beyond 100, doesn't it? How can you have something that is more than 100% saturated? How does that work? All right, have you ever made a glass of iced tea? Okay, we call it down here in the South, we call it sweet tea. And of course, we put the sugar in before we ice it up, right? We put in the sugar when the solution is hot. Why do we do that? That's right, because if we do it when it's hot, we can dissolve that sugar a lot more quickly. Have you ever taken a glass of tea, iced tea, it's already cold, and you add more sugar to it? Now, I'm not talking about them artificial sweeteners. I'm talking about real sugar. What happens when you put more sugar in it? It doesn't dissolve. It all just accumulates right there at the bottom. You get this big old slug of sugar at the bottom of the tea. That's because the sugar, the tea is already oversaturated. It's already got enough sugar in it. It's got all the sugar it can hold in the tea. So whatever sugar you add is just going to go down to the bottom and not get dissolved. It's the same way with gases. Once the solution already has as much gas as it can hold, it can't hold no more. Okay, so what this is telling me when I look at this here graph, okay, with these different kinds of solutions, is that that's the most oxygen that particular solution can hold. It can't hold no more. So when we say saturation, okay, percent saturation, that's as much oxygen as it can hold. All right, so look at this now. When we looked at our first two again, okay, so remember, salt water could only hold 85%. But the turbid water, it could collect 92.5%. So that means that turbid water can hold more oxygen than salt water. Well, it's the same reason that your iced tea can't hold any more sugar. It's already got as much as it can get. Okay, because when you dissolve salt in the water, it's taking up space. And if it's taking up space, where's the oxygen going to go? So if you got 92.5% saturated, have you got any room for oxygen? No, because there's no room. It's turbid. There's all kinds of little particles floating around in there. So there ain't no room for any more dissolved oxygen. There, see, you got it now, don't you? So saturation tells me how much is already there. I can't add any more oxygen to something that's already saturated. All right, so that's what you need to keep in mind when you're answering them questions. Okay, hope you don't mind the accent, because I have fun. I like to have fun with my accents. So, and you can't talk about sweet tea without having an accent, right? So, saturation has to do with the amount of oxygen that could go in, or what's already in the solution. Okay, so salt water, 85% of it is already taken up with salt. So very little oxygen can get dissolved into that. Turbid water's got all them little particles floating around in there. So you can't get too much more oxygen in that water. So it's not going to have a good dissolved oxygen level. Okay, so now your task is, of course, we got this hot water and this cold water over here. So what do we think about those? What's going to make them, how are they going to measure in terms of solubility? Now, keep this in mind while you're thinking. What are the particles, what are the little oxygen water molecules doing if the water's hot versus if the water's cold? Okay, think about that while you're thinking on them questions, okay? You got it? I think you do. I think you do. I think you got it, okay? Now, got any questions on this dissolved oxygen thing? I know it's a little tricky. Don't stress. Don't stress. Just call me or text me if you got a question, all right? Now, we're going to have to get back to our permeability. So I'll be back with you in a little bit with the answers to our permeability, all right? There you go. You go have a glass of sweet tea and think about it. All right, bye.